Welcome to lecture number 78, and we have been discussing about DC motor. Now, all said and done that a machine can have series winding, compensating winding, interpole winding. Now, we will first consider simple machines, and although those series field and interpole can be incorporated, some problems if you solve it will be clear how to handle that. But in my last lecture I told you that if it is a separately excited DC motor, how to work out the problem, and I assume that armature resistance drop, if it is neglected, then it will be very elementary calculation. Now, today what I will do is this: suppose armature resistance is there, separately excited DC machine, how to handle the problem? Separately excited DC motor we are discussing. As I told you, generators are nowadays not so popular at all, okay, with DC, but motors are still in use. And this is the diagram, and this is the field winding. Okay. Let us try to understand what I am telling. Suppose it is motor mode and it is running in this direction N, and this motor is to be supplied from its rated voltage, armature voltage, and this is the field voltage, separately excited. This is the field current. Okay. Now, suppose I say we find and in which direction electromagnetic torque is operating. In case of motor, electromagnetic torque is this. In which direction load torque? This load torque is the mechanical torque. Suppose it is running a pump, you must understand that the load on the shaft of the machine, either it is cutting something or it is raising water to a high rise building. So, load torque, against this load torque it has to run. Let initial steady state operating point, this is I A 1, I A. Let initial steady state operating point is this one, that is the machine draws armature current is I A 1 and speed is equal to N 1 and load torque is equal to T L 1 and field current is I F 1. Let me make it general, and this armature voltage applied is V A 1. Got the point? So, suppose the machine is found to operate steadily with these things, and electromagnetic torque generated is T 1. Therefore, T 1 and T L 1 must be same, that is why it is running steadily at this RPM. Acha, then what you have to do is this: suppose these are the observed things, then I will write two equations. Armature resistance is suppose R A. R A is the armature resistance. Then I will say that E B 1 back EMF, I will not now neglect armature resistance, E B 1 will be equal to applied voltage is V A 1 minus IA1 RA. And electromagnetic torque developed will be equal to some torque constant into flux into armature current. Flux is proportional to field current IF1 into IA1. This will be the two fundamental equations, straight away write down. This is equation 1 and this is equation 2. Got the point? Initially this thing is happening. And also note that this EB1 is equal to the constant kg into IF1 k phi into N1. This is equation 1, and here I will write it as this equal to load torque TL1. This is one thing. Now, suppose I change some applied voltage across the armature or field voltage or field current or load torque, all things I have changed, perturbation I have done. Then the second operating at second steady state operating point, suppose this quantities becomes, I find okay, next time it is drawing armature current I2, machine is running at a speed N2, load torque is suppose TL2, electromagnetic is T2 and field current is IF2 and applied voltage across the armature is VA2. Okay. In that case, I will say that EB2 will be equal to applied armature voltage, which I have changed VA2 and steady armature current is IA2. Suppose I have not changed armature resistance, also that I could include here earlier, because I could always connect external resistance in the armature. Anyway, let us not complicate this too much, and this should be equal to then kg back EMF is k into field current IF2 into new steady state speed N2, and the torque equation T2 developed by the machine will be equal to kT, the torque constant, into IF2 into IA2, and this must be equal to TL2 load torque, is not? This is 3 and this is 4. So, what I am telling? Separately excited motor, this is the general condition, applied voltage VA, IF, this one. Suppose I observe that the motor is running at a steady condition, drawing an armature current IA1, running at a speed N1, load torque is TL1 and it must have developed same electromagnetic torque T1 and TL1 are same. That is why it is running at a constant speed. IF1 and VA1 are the corresponding field current and armature voltage. The moment I know these things, these two equations can be written. What is the back EMF? What is the torque? Suppose I have played with the field current and this armature voltage, changed them, and new condition is I find it is running once again steady state condition at RPM N2, IA2, TL2, IF2, VA2. Once again write down these two equations, back EMF and this. Then what will be your next step is to calculate, take the ratio of this, I will write it here, next page. So, take the ratio of EB1 by EB2, invariably you do this. This will be equal to VA1 minus IA1 RA, VA2 minus, this is IA1, IA2 into RA, and this is nothing but your Kg into IF1 into N1 divided by this one is Kg into IF2 into N2. And obviously, I have neglected saturation, That is, I have assumed phi is proportional to IF, then only you can do that, otherwise. K phi n is the voltage. So, phi can be replaced by some other constant into IF. So, this is this you get by dividing 1 with 3 of the previous equation. Then divide equation 2 with 4. If you do this, you will get T1 by T2 is equal to Kt phi into Ia, phi is proportional to If. So, Kt into If1 into Ia1 divided by same constant Kt If2 into Ia2, and this must be equal to TL1 by TL2. Got the point? Load torque, mechanical torque present on the shaft of the machine may also depend on speed. I do not know. If I say that it is a constant opposing load torque, then TL1 and TL2 will be same. If I say load torque is proportional to n square, if suppose load torque remains constant, is constant, then I will say TL1 has not changed, TL2. It may so happen, this is one, it may so happen if load torque is proportional to n square, then TL1 by TL2 will be equal to N1 square by N2 square. Got the point? N1 square by N2 square. So, this thing is known. Therefore, with these two sets of equation, if I know the first operating point completely, and if I say that I have changed the armature voltage as well as field current of the shunt machine, what will be the new armature current drawn if it is like this, it can be easily solved by using these two equations. These two are the most fundamental equations we have to solve in case of DC machine and take the ratios, that is back EMF equation and the electromagnetic torque equation, and we can solve problem. So, with this in mind, I will now tell you. So, this in fact, you can start solving several problems in DC machines by using these two equations, provided phi equal to IF. Only one point of caution: if somebody says that phi is not proportional to IF, then one has to, you must understand this, that the equation of the generated voltage E g is something like this. It is not straight, and this is your IF. If it is not directly proportional to IF, then I must have this information to get the ratio of the back EMF. Okay, at this RPM, this was the field current. Then those EB1 and EB2 are to be used, because EB1 and EB2 are nothing but the generated voltage. Suppose this OCC I will refer to, it is at a given RPM n. Then for any value of field current, I will be able to tell what is the induced voltage. If it is IF1 and if it is running at N1 RPM, from this OCC only I will be able to tell that. We discussed this earlier. Therefore, in that case, this open circuit characteristic is to be used to correctly predict this one. But otherwise, in general, you can assume that phi is proportional to IF in the linear zone is machine is operating. Then these are the two equations, back EMF and the torque equation, because in steady state electromagnetic torque and load torque must be same in case of motor. If this is the direction of rotation, this is the direction of electromagnetic torque, and this is the direction of the load torque. Steady state T must be equal to T L, so that it runs at a constant RPM n. That is the thing. Okay. Now, what I am going to tell you, that I do not care whether the machine is connected as a separately excited motor or a shunt motor, those fundamental equations will be equally true. For example, a shunt motor, what is the connection? This is the armature, this is the field current, field, these two are connected in parallel, and here you give supply voltage. Here no point in distinguishing between the voltage applied across the armature and the field, they are in parallel. Na? So, this is V. Shunt generator, to generate voltage, there are several steps, I told you. In case of shunt motor, do not care, because you are injecting current. Here this voltage is well defined, there will be some field current flowing here, there will be some armature current flowing here, and suppose the machine is running steadily at this RPM, then this current drawn from the supply is called the line current, and this will be divided into two halves, IA and IF. So, IL line current is equal to is equal to IA plus IF. This will be the load current. Okay. And what is there here? RA and back EMF. So, all the equations where there I wrote is valid. What will be back EMF here? EB1. It should be equal to supply voltage V minus IA RA general when it is drawing current, and electromagnetic torque will be proportional to kT into phi, but phi is replaced by field current if it is linear into the armature current. I do not write 1, 2. Now, I know what it is, and this I will write it as some kg into IF into N, and this one is equal to your load torque. This is the general. Now, no point in elaborating the same steps if it is at some applied voltage this that armature current was 1, you replace it by 1, 2 etcetera, take ratios. So, the point I want to make is those two relations irrespective of the connection, series, shunt, whatever it is, these two basic equations must be satisfied, and that will be the starting point for solving any of the problem. Acha, if you are following me correctly, suppose I say that in this DC machine RA is vanishingly small, suppose I say. I am just asking one simple question, RA is equal to 0, vanishingly small, you neglect the IRA drop compared to the applied voltage. Suppose applied voltage is 200 volt. Okay. Then what will be the back EMF of the machine? Then back EMF of the machine will be 200 only. And when I say 200 only, no matter at what speed and what armature current it is drawing, because IRA drop is negligibly small. Suppose here I have used very good conducting material for armature, that resistance is very small. Then you must understand that the back EMF is going to be V. Perhaps I am playing with field current, but I will always state that back EMF, okay, it is fixed. If back EMF is fixed, and suppose initially you have applied 200 volt. Now, let me that problem let me ask you now that V1 I have applied is 200 volt. Okay. Field current initially is some IF1, and initial speed of the machine is suppose 1000 RPM. Now, I say that I will make the and machine is found to run steadily at this RPM. IF1 has got some value. Suppose I say that I make the applied voltage, that is this voltage V 2 to 50 volt, and ask you what is the speed at which the machine is going to run. In this case, E B 1 is equal to 200 volt only, because IRA drop is neglected. $200 volt. In the second case, what is EB2? EB2 will be how much? Once again 50 volt. I have reduced the voltage by this amount. Therefore, EB2 by EB1 will be equal to 50 by 100 approximately, that will be the thing, and this is equal to 200, thank you, and this is equal to kg into IF2 into N2 by kg IF1 into N1. This will be the thing. Now, if this current was IF1, what is the field current here? IF2? See, this is the beauty of shunt field connection. How much will be the field current? You have reduced the voltage by 4 times. So, your IF2 has to become equal to, because field resistance I have not varied. So, IF1 by 4 it will be. So, IF2 by IF1 will become, so this is equal to 1 by 4, no doubt, is equal to IF2. What is the speed N2 I am looking for? Kg goes IF1 and initial speed is 1000 rpm N1, is not? And this is equal to 1/4 or 1/4 is equal to this. But IF2 by IF1 is also 1 by 4, N2 by 1000. Therefore, the speed at which the machine will run is also 1000 rpm, speed will not change. It is no surprise, because the field current is also reduced by a factor of 4. Therefore, you see, whether the machine is connected in shunt or separately excited motor, only thing you draw the circuit correctly and write down these 2 equations, back EMF and armature equations. And from this load torque, see here load torque does not come into picture provided R A is equal to 0, but it will come into definitely, and I have to take the equation of torque. There I do not have to write the torque equation, I am getting this thing as it is. So, V minus IARA. So, often to get the quick results, you neglect RA and quickly calculate, okay, and back EMF will remain same. Got the point? So, this is how the calculation will go on in series and shunt machine. Why I have told calculations first before discussing the speed control, various methods of speed control of DC motors as well as starting phenomena is and braking, is that the calculations in DC machine are very simple. I have assumed it is running at steady state. How it reaches steady state, that also I will discuss, but first thing is this one steady state, this is the thing, and you can carry on calculation. So, several problems once again you can solve on your own and solve it and enjoy reading, analyzing DC motors. Okay? We will continue with that.